the flux coming out of that particular area will solely depend on the amount of charge or the magnitude of charge. Any surface which agrees with the symmetrical arguments, which means that if we take a particular distance, the symmetry should be kept, so the electric field does not change. There are electric fields like this, kept in an electric field like this, and the electric field is represented by the letter E, or the magnitude of the electric field is represented by the letter E. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, Mysuru. And we were discussing about electric fields and electric charges. And in this class, we'll be discussing more on that topic. So we were discussing about electric charges and electric fields. So what happens when an electric charge is kept in an electric field and how it behaves and what is the properties of electric fields and how a charge behaves. And finally, we were discussing about dipoles. And let's carry on from that moment. We know that a dipole is nothing but two charges which are equal in magnitude but opposite in polarity. That is, one will be positive and one will be negative, but they will both be having the same amount of charge. And they will be separated by a distance of 2a. And the dipole moment of that dipole will be given by P is equal to Q into 2a. And this is a vector quantity and the direction of the dipole moment will be from negative q to positive q. So these are the things we knew and we found out. And we found out what happens when we select a point along the equatorial plane or the axial points and what will be the electric field along that diagonal. So now the question arises, what if the entire dipole itself is kept in an electric field? How will the dipole behave? So let us look into that for a moment. So let's imagine that this is our electric field. Let's imagine that this is our electric field and we have a dipole which is kept like this. So one will be negatively charged and one will be positively charged. And this is our dipole and we know that the distance, let's say this is A and this is B. So we know that the distance AB is 2a, which is the length of the dipole. And this is the electric field applied, which is in this direction. So when a charged particle is kept in an electric field, it experiences a force. So the positive charge will always move towards or along with the electric field or along the direction of force of the electric field. So this positive charge will be experiencing a force in this direction and this negative charge will be experiencing a force in the opposite direction because they are equal and opposite charges, equal in magnitude, opposite in polarity. So this will be the force experienced by the charges. So what happens then? So what happens when a dipole is kept in a uniform electric field? You can see that the field is uniform. It is not like one area is dense and one area is rarer. It is a uniform field, which means that the intensity of the electric field is uniformly distributed. So the question arises, what happens to the dipole which is kept in the uniform electric field? So imagine that there is a long stick. This long stick is being pulled to one direction and the other direction at the same time with equal amount of force, but in opposite direction. So what happens when you have a long stick, one is being pulled in this direction and the other one is being pulled in this direction. So it undergoes rotation because this is being pulled in this direction. So this goes that way and this is being pulled in this direction. So what happens is that it goes in a circular path. So force experienced in a circular motion or in rotational manner is known as torque. So it experiences, or this particular dipole will experience a torque. So just for namesake, just understand that when a dipole is kept in a uniform electric field, it will experience a force. The positive charge will experience a force along the direction of the electric field, while the negative charge will experience a force in the opposite direction, and that will cause the dipole to spin, or it will try to attain a position of minimal energy state where the tension is low. Again, I told you, no particle in the universe wants tension. So they want a state of minimal energy. So for that, they will align themselves in order to reduce the force being applied on that particle. In this case, it will be aligning parallelly to the electric field so that the forces cancel each other out. Equal force will be exerted in that direction and equal force will be exerted in this direction. So what will happen? If it is at an angle initially, it will start to spin or it will start to rotate in the direction of the electric field just because it is being pulled in both directions. So if this is a dipole and this is kept like this at an angle, this will experience a force and it will start to rotate. It will start to rotate. Okay. So our job here is to find out what is that force, what is the amount of force that is being exerted on this dipole. So we are going to find out what is the force exerted on the dipole. So we know that electric field is the force experienced per unit charge. So it is the force experienced per unit charge which is being discussed in the earlier topics and we found that out. And we know the equation for the force which is K Q1 Q2 divided by R square, or we can say this is capital Q for simplicity's sake. So we can say that the electric field will be equal to K capital Q divided by R square. So it is simply KQ by R square. So we know the force being exerted will be equal to KQ divided by R square, and here also it will be equal to KQ divided by R square, and the only difference is that one force will be acting in the opposite direction to the other force because of the difference in polarity. So that is the only difference that is here. So from this equation we know that electric field will be equal to the force experienced per unit charge, or from this we can find the force which is equal to F will equal to Q times E. That is, the charge times the magnitude of the electric field will give you the force. So we can say that the force will be equal to Q times E here, and it will be equal to Q times E here also. The only difference will be that these forces will be in opposite direction. One will be acting in this direction while the other force will be acting in the opposite direction. That is because of the difference in polarity. Okay, so we now found out that the force will be equal to Q times E. So let us keep that aside here and we call that equation number 1. So we know that the force will be equal to Q times E. So what are we going to find out actually? We have to find out torque, which is represented by the Greek letter tau. Okay, we have to find out the torque which is acting, because even though the force is acting in opposite directions, the dipole is going for a spin and we are calculating the force in the rotational sense which is given by torque. So the equation to find out torque of any particle is that it will be equal to the force applied, and force applied times the perpendicular arm distance. The perpendicular arm distance will give you the torque, which means that we already found out the force which is applied on this dipole. Now we only have to find out this perpendicular distance. Okay, you only have to find out this perpendicular distance. For that, it is very easy, because to find out this, what I did was I extended this force line backwards and I drew down from this positive dipole so that it meets at a point and that point makes a right angle triangle. So that we can say that ABC is a right angled triangle. Triangle ABC is a right angle triangle. So from triangle ABC, we have to find out the length BC. So we don't know BC for now. So let's just mark it as X. And let's say that the dipole is being kept at an angle. It is not kept upright. It is kept at an angle. So let's say that the angle is theta. The angle between the dipole and the electric field is theta. If this angle is theta, automatically this angle will also be theta due to geometrical concerns. So we can say that this angle is theta, or angle BAC is equal to theta. If angle BAC is equal to theta and this is a right angle triangle, then we can say that the adjacent side is nothing but cos and the opposite side is nothing but sine, because base square plus altitude square equals hypotenuse square. We have already seen this in the last class. So we can say that sine theta, I'll write it here, sine theta will be equal to x by AB. X by AB. But we already know that AB is the length of the dipole, and the length of the dipole is given by 2A. So AB is equal to 2A. So we can substitute that and we can write it as x divided by 2A. From this, we can find x as x will be equal to sine theta 2A. So this will be the length of this side, that is sine theta 2A. Let us keep that as equation number 2. So the first equation is that force is equal to QE, and the second equation is that the perpendicular arm distance is given by x is equal to 2A sine theta, or sine theta into 2A. So to find out torque, the only thing we needed was force into perpendicular arm distance. So we can say that force was already found to be QE, and then we found the perpendicular arm distance, which is x, as sine theta into 2A. And now if we rearrange this equation, we can write it as 2AQ into E sine theta. But we already know that 2AQ is nothing but the dipole moment, which is indicated by the letter P. 2AQ is the dipole moment. So we can write this as PE sine theta. So this is the torque experienced by a dipole kept in a uniform electric field, and this can be written as P cross E. Since both of these are vector products and the angle between them is sine theta, we can write it as P cross E. One quick thing to remember, if the angle between any two vector quantities is indicated by theta, then you can quickly assume that it is a dot product, and if the angle between things are sine theta, then you can quickly assume that it is a cross product. So one will be sine and one will be cross, and it is obtained through vector dynamics. And here it is, these two vectors are cross products, so P cross E, and the direction of this will be given by the right hand screw rule. That is not important. The important thing is that the torque experienced by a dipole kept in a uniform external electric field will be given by the equation P into E times sine theta, or it is the product of the dipole moment of the dipole and the magnitude of the electric field and the angle at which the dipole is being kept. Because depending on the angle, sine theta changes and the nature of the dipole interacting with the electric field also changes. So let us look at some special cases. Special cases. That is, when sine theta or theta is equal to 90 degrees, 0 degrees and 180 degrees. So what will be the difference? So let us look at sine 0. So what happens when theta is equal to 0 degrees? So in that case, torque will be equal to P cross E, which is equal to PE sine theta, that is equal to PE sine 0 degrees. So since theta is equal to 0, PE sine 0 degrees. Sine 0 is nothing but 0. So we can write this as 0, which means that there is no force being exerted on the dipole, or the dipole is not experiencing any rotational force. That means that if the electric field is represented in this direction, this is a uniform electric field, remember that. So if the electric field is represented like this, the dipole kept in the uniform electric field will be parallel to the electric field. So this will be positive, this will be negative, and the dipole will be kept parallel to the electric field, or the angle between them will be 0, and thus the dipole won't experience any force, and it will be long asleep, and it will be undisturbed, and it will be very peaceful. So if the angle between the dipole and the electric field is 0, then the torque experienced by the dipole will be 0, which means that it is not experiencing any torque, or it is not experiencing any force to rotate. Because what a dipole will do actually is that when it is at an angle with an electric field, it wants to reduce that state of stress, and it wants to have a minimal state of energy or minimal state of exerting a force. So for that, it will align in such a manner that the force exerted or the torque experienced will be 0. And this is the most perfect state for that. Hence, it is known as a stable state, stable equilibrium state. This is known as a stable equilibrium state. And the other thing is that, so what happens when theta is equal to 90 degrees? So what happens when the torque experienced by a dipole is PE sine 90 degrees? So that means that if again this is the electric field, then the dipole will be like this. One will be positive, one will be negative, and the dipole will be kept vertically like this. So what happens? Imagine that the electric field is water flowing. So this is water flowing with great force. So let's say that you are in a water theme park like Wonderla or something, and you have experienced tidal waves, right? So just like those tidal waves or that wave pushes, electric field is being exerted in this direction, and imagine that you are the dipole kept like this. What will happen? You will obviously experience a force, and for the dipole, since the force experienced is torque, it will undergo a rotational motion, which means that the dipole will tend to rotate, and in this state the force experienced will be maximum because sine 90 is equal to 1, which means that tau is equal to P times E, which means that maximum torque is experienced when the dipole is upright, or the angle between the dipole and the electric field is 90 degrees. And finally, what happens when theta is equal to 180 degrees? So what happens when theta is equal to 180 degrees? Again, we have the electric field like this, and the dipole is being kept in the electric field. So we have our equation tau is equal to PE sine theta, or P cross E, and sine theta here is PE sine 180 degrees, which means that negative PE. What does negative PE means? I don't understand it. What does negative PE means? Torque is equal to negative dipole moment times magnitude of electric field. What does that mean? So in physics, in order to understand an equation, or to understand what the equation is trying to communicate with you, you should pay respect to the entire equation. Here, the sign is indicating that the direction of the dipole is opposite in nature, which means that the dipole is flipped. So initially this was a negative charge and this was a positive charge. This is now flipped, being this being a positive charge and this being a negative charge. So it is in a state of equilibrium, sort of, because this is an unstable equilibrium. Why? Because the positive charge is experiencing a force in this direction, but the negative charge is experiencing a force in this direction. So even though the dipole is parallel and it is kind of stable, it is an unstable equilibrium. And that is what happens to a dipole which is flipped. And this will be the torque experienced by that particular dipole. So we have seen three particular cases where tau can be equal to minus PE when sine theta is 180 degrees, or tau is equal to PE where theta can be equal to 0 degrees. And finally, we have also seen that tau can be equal to 0 when the dipole is parallel to the electric field, or theta can be 0 because sine 0 is 0. So to summarize that, it will be very easy. That imagine that you have an electric field and you have a dipole which is kept at an angle, and let's say this is negative and this is positive. So positive charge will experience a force along this direction and negative charge will experience a force along this direction. And from the field equations, we already found out that E is equal to F by Q, or here it is F is equal to QE. We found out that. So we know that the force experienced, F will be equal to Q times E, and F is equal to Q times E, both equal in magnitude but opposite in direction. And since it is under an electric field and these are opposite charges, the dipole will undergo a rotational motion, which means that it is experiencing a force in rotational terms, which is represented by tau, and tau is nothing but force experienced by that particular particle times the perpendicular arm distance, and that is here given by this distance. So this will be 90-degree angle, and if this angle is theta, this angle will also be theta due to geometrical concerns, and we can say that the force experience can be found out. We already found out that the force experience will be equal to Q times E, and to find out this distance, which is x, we use the Pythagorean theorem, which states that if this is cos and this is sine, sine theta will be given by opposite side divided by hypotenuse, which means that the hypotenuse is nothing but the length of the dipole, which is 2a, and the unknown side is x. So x by 2a will be equal to sine theta, and sine theta times 2a will be equal to x, and that is the perpendicular arms distance, which is sine theta times 2a. And if we take this 2a and this q together, we will get the moment of the dipole, which is represented by the letter P, and that will be equal to PE sine theta, which can be again represented as P cross E. And both of these are vector quantities, and this will be the torque experienced by a dipole kept in a uniform electric field. And we discussed about the special cases when theta is equal to 0 degrees, 90 degrees and 180 degrees. That is all about dipoles. Now, since we have passed dipoles, let us move on to a new thing, that is Gauss's law or Gauss law. So what exactly is Gauss law and how are we going to find that out? So let us go back to fields. You will always go back to fields. I don't know why. So let us go back to fields. So what was an electric flux actually? So if this is a surface and there are electric fields like this, kept in an electric field like this, and the electric field is represented by the letter E, or the magnitude of the electric field is represented by the letter E. I am taking a small division here, a small area there. So to represent it is a small area, we'll take it as dA. And if you take that particular region, there will be a normal for that. It is represented by n caps. So for that particular region, if we zoom in, it will be like this, and here there will be a normal vector. There is a normal vector because the angle between the electric field and the normal vector determines the equation. So that is why this angle is important, and that is why we take the normal vector. So there is a normal vector, and this will be the electric field coming out of that, and it will make an angle between the normal and this will be the electric field. The angle between them, let's say it is theta, and the electric field is E. So the electric flux phi will be given by E dA cos theta. And It is said that you should add an n caps here to indicate the normal vector, but it is fine. So you can erase this n caps and this is enough. So this will give you the flux for that particular area. But my problem is that this is a very small area. So in order to calculate the whole surface, I have to take small pieces like this until the entire surface is covered. And that is very difficult, taking each piece and adding it together. So to fix that problem, we have a solution in mathematics, and that is known as integration. So if you have very small bits of elements, you can integrate it to a big thing using integration. So differentiation means cutting something into very small elements, and integration means the quite reverse of that, which means building something from very small pieces. And imagine that you have a desk, you cut it into small pieces, and that is differentiation, and you take the small pieces and you build a desk, that is integration. So we can integrate this and we will get the total area, which means that phi is equal to, electric field is constant here because it is not changing suddenly. So we will take out the electric field and integral dA, and cos theta also can come outside. So integral dA will be equal to A. So we can write it as EA cos theta, or simply E dot A. So this is the equation to find the flux through anything. Let's say we have a point charge or a positive charge Q, and it is inside a sphere. It is inside a hollow sphere like this, and we want to find out what is the flux at the surface. Let's say this is dA, and we want to find out what is the flux there. And obviously, if we take a small element, there will be something perpendicular to it, and that is known as n caps. And the flux will be coming out of that, and it can make an angle with the n caps. So that is why the cos theta is there, just so you don't forget about that. But anyways, let's say this distance is r. Okay, don't forget, this is not a circle, this is a sphere. So the distance from here to here and here to here is both r. That is because the sphere is in 3 dimensions, so that this is a surface area dA, and the distance from anywhere to the surface is represented by the radius r. So if this is a sphere, we are just taking an area around here, and it is being represented in 2-dimensional form. That is why you think this distance is less, but this is actually an area on the surface part. So in order to find the flux there, we can say that phi is equal to the magnitude of the electric field times the area we have chosen and the angle between them, or simply we can write it as E dot dA. So I told you before, to find the entire electric field or electric flux radiating out of this entire surface, we can say that we can find it using integration. So integral E dot dA will give you the entire flux, which is nothing but EA, and here the A stands for the area of this particular sphere, and the area of a sphere is given by 4 pi r square. So 4 pi times the radius squared will give you the area, and if you want the volume, then 4 by 3 pi r cube will give you the volume. For now, we only need the area, so we can write it as 4 pi r square into E. So we can say that 4 pi r square E will be the electric flux. Electric flux is radiating out of the sphere, and this electric flux or the flux will be equal to how much ever the area of that sphere is times the magnitude of the electric field which is being experienced there. So if you had taken a closer look, let's say this was the sphere and this was the small area we have taken dA, and we found out that, so this was the charge, so we found out that flux phi is equal to E times A, and the area was 4 pi r square, and we know what E is. So E is equal to KQ divided by r square, and K is equal to 1 by 4 pi epsilon naught Q by r square. We will substitute this value into E, and then we will get this as the initial 4 pi r square, because this r and this r are same. So 4 pi r square times Q by 4 pi r square epsilon naught. And the 4 pi r square cancels each other out, and we will get the equation as phi is equal to Q divided by epsilon naught. So just keep this in mind. It means that if we have a point charge which is Q, the electric field or electric flux coming out of that will be solely dependent on the charge of that particle, which means that if this is a +2 charge, then the field or flux, the flux coming out will be like this of a sphere, and if this was a +5 charge, then the flux coming out of this will be much more stronger, and that is solely dependent on the magnitude of the charge and is independent of the area. It does not matter that if I choose a perfectly symmetrical sphere or if I choose a crooked structure such as this, it does not matter, because the flux coming out of that particular area will solely depend on the amount of charge or the magnitude of charge. So that is all about flux. So a guy named Gauss and a guy named Maxwell also researched on the fields and electric charges, and they found out that the electric flux through a closed surface was equal to be E dot dA. So integral E dot dA is equal to be Q times epsilon naught, which means that the flux coming out of a closed surface was equal to the amount of charge that was enclosed in the system. That means that if there was n number of charges, that much was the flux. If there was no charges, then there was no flux for a closed surface. Why a closed surface? Because it should not be influenced by other charges. If it's an open surface, if it's an open system, other fields can interact with it and it will become more messy, and this law won't hold. So we can say that electric flux for a closed system was found to be Q divided by epsilon naught, or the net charge determined the amount of flux coming out of that particular closed area. So, and this charge can be not just one charge, it can be a variety of number of charges. So we can say that the net amount of charges or the charges enclosed, which means that if we consider a surface like this, any surface, and there are n number of charges distributed like this throughout the surface, then we can say that the charges enclosed by this closed surface will directly influence the amount of electric flux which is emitting or coming inwards or outwards depending on the charge. If it is positive, it will go outwards, and if it is negative, it will be inward. So the flux will be determined by the amount of electric charges enclosed by that particular closed region. And this was stated as a law by a guy named Gauss, and this is known as Gauss's law or Gauss law, and it states that the electric flux phi will be equal to the net charge enclosed by a surface divided by epsilon naught, and this should be a closed surface. So this is Gauss law, and Gauss law states that the flux of a closed surface will be equal to the charge enclosed by that surface by epsilon naught. And what does this actually mean and how can we use this will be discussed shortly. For any closed surface, we can use a symmetry argument and we can determine the flux coming out of that particular region. Let's say that you have a line of charge. Let's say you have a wire which is completely charged and you want to know what will be the electric field at a point away, let's say P distance or R distance away from that particular charged element or charged wire. And let's say somebody accidentally knocked a wire onto a sheet of, let's say metallic shield is now completely charged and you want to know what will be the electric field around that sheet, or let's say this distance away from that sheet, and you want to find out that. Even if you don't want to find out, maybe some people want to find out such things. So for all this, we can use Gauss law and find out the electric field of a closed surface using the Gauss theorem. This is also known as the Gauss flux theorem. So before moving on to the applications of the Gauss theorem, we must discuss one important thing, that is charge distribution. So we will be discussing about charge distribution. So what exactly is this charge distribution? Charge distribution can be of two types. That is, it can be distributed unevenly. That is, some charges will be randomly spread and some will be concentrated on particular regions, and this is unevenly distributed. And there is another possibility where the charges are equally distributed. It is distributed symmetrically, equally around all points. So this is an evenly distributed charge carrier, while this is an unevenly distributed charge. So if you have a material like a rubber or an insulating material, charges will be concentrated on some points and it will not be present in every point equally. But if you have a conducting material, charge distribution will be even throughout. So that is one thing you have to remember. And the another thing to remember is that I told you that it is not just one charge on a particular particle. If you have an electric wire or if you connect electricity to pass through a wire, it is not just one charge in that wire, it will be a number of charges. There will be millions and billions of charges. The number of electrons in your body is itself in billions. So it is not practical to say or find equations for just one particle or one charge, or let's say n charges. So we have to consider equations that fit the practicality of the problem, which means that we have to consider density of the charged particles, which means how much charge is spread throughout a particular given area. So density is given by mass by volume. Instead, we are going to find out the charge density. Charge density is nothing but how much charge is distributed per given area. So depending on the element or depending on the shape you are choosing, the charge distribution will also differ. If you are choosing a sphere, let's say you are choosing this evenly distributed sphere, then the charge distribution will be different compared to a wire you are choosing. So compared to this, the area of these both shapes are different. So the charge distribution will also be different. So we'll discuss that and why we are taking a charge distribution which is even or which is evenly distributed is because we have to keep the symmetry arguments in place. We cannot have electric fields to be different in a shape like this, because if the charge carriers are concentrated in one side and is absent in certain areas, the electric field in points will be different. And we cannot have that, and we cannot apply Gauss's law if this is the case. So that is why we have to meet the symmetry arguments and we have to choose charge which is evenly distributed. So again, we will find out the charge density of materials. So we will be finding out surface charge density, linear charge density, and finally volume charge density. We'll be finding out surface charge density, linear charge density, and volume charge density. So what exactly is surface charge density? Imagine that you have a sheet which is charged evenly, that is, it is charged evenly throughout. Then we can say that the charge density of this particular sheet is, let's say it is denoted by sigma, then sigma is equal to the amount of charge distributed throughout this sheet. Let's say capital Q is equal to Q1 plus Q2 plus Q3 plus Qn. So n number of charges are added together divided by the area of that particular sheet. If it is a rectangular shaped sheet, then we can say that it is L into B. If it is a different shape, we can say that it is a different area. For now, it is Q times A, and that is denoted by the letter sigma. So we can say that surface charge density is equal to, or is given by, sigma is equal to Q divided by A, or sigma A is equal to Q. Surface charge density times the area will give you the net amount of charge enclosed in that surface. So why did we actually learn about all these things? We learned about all these things and this charge density so that we can apply Gauss's law in different cases. Let's say that you have an infinitely long wire. It is a really long wire and the charges are distributed evenly. Let's say it is positive charges. So it is distributed evenly throughout this surface. And you are asked to find out what will be the electric field at a point P, which is r distance away from the center of the wire. So what will be the electric field at that particular? Imagine that a random dude or random person just came up to you and asked, what will be the electric field of a charged wire at r distance away at a particular point P? I know that is unlikely to happen, but what if? I mean, anything is possible, right? So you can actually say that you can actually use Gauss's law to represent this particular thing, and you can actually say, in order to find out the electric field at that particular point, first you have to imagine a Gaussian surface. A Gaussian surface is used to prove or state Gauss's law. So it is a closed surface around a particular region that encloses a net amount of charge. So since this is a linear element, we are considering a Gaussian surface which is a cylinder. A Gaussian surface can be any surface which agrees with the symmetrical arguments, which means that if we take a particular distance, the symmetry should be kept, so the electric field does not change. So first we have to consider it is a linear charge density element. So lambda is equal to Q by A being the area and Q being the charge distribution. Just don't forget about this thing. So just let's keep it there. Since it is a wire, we have to take linear charge density. And let us consider 2 points. Since this is infinitely long, we cannot go up infinity to down infinity. So we are taking a point, let's say this is P1, and we are taking another point up here, which is P2. So this will be infinitely long, which is charged. So we are just taking a point P1 and P2 at particular points. And we are saying that the electric field at P1 and P2 will be equal to E2 and E1 respectively. Just so we are just assuming that there are 2 points P1 and P2 and there is an electric field by that, and that is E1 and E2. Don't worry about that. They will take care of themselves. We'll see that why. So we know that electric field is a vector quantity, and we can say that the total electric field E will be equal to, let's write it here, the total electric field E will be equal to E1 plus E2. Just remember that and just keep it here. So in order to prove the Gauss's law or apply Gauss's law in this particular case, we have to have a closed surface which encloses a net amount of charge. So here you are going to imagine a Gaussian surface which is a cylinder, because you can also imagine a sphere, it doesn't matter, but for, let's say, calculation purposes or for mathematical reasons, a cylinder will be much more easier and cool. So we are imagining a cylinder here. So this is the base of the cylinder, and let's say this is the cylinder. So we are going to calculate what is the amount of flux coming out of this particular cylinder. And yeah, you can see that the point P is coinciding with the surface of the cylinder. And if you imagine that this is the base of the cylinder, this circular area is the base of the cylinder, and this is the top portion of the cylinder, the amount of electric field coming out of that way and this way will cancel each other out. Or we can simply put it that the vertical components of E1 and E2 will cancel each other out, and there will only be this particular component, which is horizontal components. That is all for symmetry arguments. So just imagine that there is an infinitely long wire which is charged and it is evenly distributed. You imagined a point P which is r distance away from the center. Then you took 2 points P1 and P2 because it is infinitely long and you have to have reference points, and the electric fields at that point is E1 and E2. Then you considered a cylinder shape in order to apply Gauss's law. Just keep it there. And we know that the Gauss's law is given by phi is equal to Q by epsilon naught, and phi is also equal to integral E dot ds or dA. We'll take dA because it's area. So in order for Gauss law, it has to be a closed surface. So this has to be a closed surface. Now this is a closed surface, everything is closed, so we can have the system inside that. So in order to represent that closed surface in this equation, we can write it as integral, put a small circle, because this will represent a closed loop. So this is a closed surface, and closed surface E dot dA will be equal to Q by epsilon naught. So Gauss's law can also be represented by this manner. So you can actually write a surface integral, because we are taking the surface integral of this, we are just taking the area. Otherwise, just putting a naught on the integral sign itself is enough. You can say that phi closed is equal to closed integral of E dot dA, which is equal to Q by epsilon naught. So this is actually Gauss's law in this case, and we are going to apply that here. So we know that closed surface integral E dot dA phi, we are going to find out the flux coming out of that area. So phi is equal to E dot dA, which is nothing but Q by epsilon naught. So you might think that I don't know anything in this equation, but you actually know what Q is, because we know that linear charge density is nothing but lambda is equal to Q by A. We can write that as lambda times A will be equal to Q. So we have an equation for Q. So we can write that as closed surface integral E dot dA will be equal to lambda A divided by epsilon naught. So for a linear charge density, it is not actually represented by area. So if you have an infinitely long wire which is positively charged or which is evenly distributed with charges, then this length is the one which is being considered. So charge density lambda is equal to total amount of charge divided by the total length. It is the total amount of charge divided by the total length. So we can write that as lambda is equal to Q into L. And we can say that closed surface integral E dot dA will be equal to lambda times L by epsilon naught. And the thing to be remembered here is that since these vertical components this vertical components are opposite in direction and they cancel each other out, we are only considering this particular curved surface area, and then we can say that E into the area, which is nothing but 2 pi RL, will be equal to lambda times L divided by epsilon naught. And you have an L here, you have an L here, you can cancel that out, and you finally rewrite that as E is equal to lambda by 2 pi epsilon naught R. So this will be the electric field of an infinitely long charged wire. And the thing to be noted is that if the wire is positively charged, the equation will be positive, and if the wire is negatively charged, the equation will be negative. That just indicate that the field lines are coming out or going in. So if it is positively charged, it will be coming out, and if this was negatively charged, the field lines will be going inwards. So that is the only difference here. Finally, to summarize, it is nothing but if you have an infinitely long wire which is charged, let's say in this case it is positively charged, first we will have the linear charge density, which is given by lambda is equal to Q by L. Don't forget, it is not Q by A, that is for surface charge density. If you consider a surface, you will consider area. If you consider linear charge density, you will consider the length. And if you consider volume charge density, then you will consider it as volume. Okay, so it is Q by L, then Q by L, then lambda L will be equal to Q. We'll just keep that aside, don't forget about it. We were finding out what will be the electric point at a point P, which is R distance away from the center. For that, we considered a Gaussian surface. In this particular case, this was a cylinder. This was a cylinder, and then the top portions cancelled each other out because we considered two reference points here, which was P1 and P2, both having electric fields E2 and E1, and the vertical components cancelled each other out, which means that we don't have to consider anything of this surfaces. So both the surfaces cancelled each other out, and then we only had to consider the curved surface. And we already knew that closed integral E dot dA was equal to Q by epsilon naught from Gauss law. So phi equals closed surface integral E dot dA is equal to Q by epsilon naught, which is given by Gauss's law. And then we know what the surface integral of this particular equation is. That is the surface integral of this particular equation, that is we are considering this small area. If we integrate that area, we'll get the whole surface of the cylinder, and that is nothing but E into 2 pi RL, and we already know what Q was because associating with linear charge density, lambda is equal to Q divided by L, which means that Q is equal to lambda times L. Lambda times L is equal to Q. So we can write it as lambda L divided by epsilon naught, and it is easily written as E is equal to, we'll bring this 2 pi RL down and cancel the L's. So we can write it as by lambda by 2 pi R epsilon naught, and that is our final conclusion. The electric field at a particular point can be found out for a linear charge density element or for a line element. It can be found out through this equation, and we found this using Gauss's law. Now we found out what was the electric field for a linearly charged element. Now we are going to find out what is the electric field for an electrically charged sheet with equal distribution. That is, we have a sheet of charge. Let's assume that a particular metal sheet was charged with positive ions like this. It had positive charges distributed throughout evenly. The entire surface is covered with positive charges, and we have to find the electric field, let's say at a point P, r distance away from that particular sheet. Now again we are going to use the symmetry arguments, and we are going to say that the surface charge density of this particular sheet is given by sigma is equal to total amount of charge divided by area. So remember, if it is linear charge density, it is lambda is equal to Q by L, and if it is a sheet, it is sigma is equal to Q by A area, and if it was a sphere, then it was volume charge density indicated by rho is equal to Q by V. So don't forget about that. So we considered a sheet of paper or a plain sheet which is positively charged throughout, which is evenly charged. And so what will be the electric field due to a plain sheet which is positively charged or negatively charged? The only difference will be the signs will interchange. But let's say what will be the electric field due to a uniformly charged plain sheet. So for that, again, what we are going to do is that in order to apply Gauss's law, symmetry arguments must be met. In order for that, we are going to consider again a particular region in this charged sheet. I am going to consider a rectangle. You can use any Gaussian surface that you seem fit. It should be a closed surface and it should meet the symmetry arguments. That is the only criteria. And then let's say this is the Gaussian surface I have chosen. So again, the vertical components will cancel and we'll only have the parallel components or the horizontal components, since the vertical components again cancel each other out. And now we are going to apply Gauss's law, which states that phi is equal to integral closed surface integral E dot dA is equal to Q by epsilon naught. And here integral closed surface integral dA will be equal to A, which is nothing but this face, let's say this face and the face at the other end. So these two faces are the only area which will be adding up, while the other two areas will get cancelled, because the vertical components will cancel each other out while the horizontal components will add each other. That is because there is a face on this side and there is a face on this side. Remember that the field lines are coming out and also in this direction and in this direction. So there will be two faces, so there will be two areas. So which means that there will be two areas here, which is face 1 and face 2, and they will add themselves, so that we can say phi is equal to EA plus EA, that is of phase 1 and phase 2. So we can say that phi will be equal to 2 into E times A, and that will be equal to Q by epsilon naught. And we know that Q is nothing but sigma times A will be equal to Q, and we can write it as 2E into A will be equal to sigma times A divided by epsilon naught. This area and this area will cancel each other out, and we can say that the electric field of a charged plane sheet which is uniformly distributed will be equal to sigma by 2 epsilon naught. So this will be the electric field due to a uniformly charged plane sheet. So what did we actually do? We actually considered a plane sheet which was uniformly charged and the positive charges were spread evenly throughout. Then we considered a Gaussian surface to enclose that charge, and we knew that the vertical components cancelled each other out and there was only the horizontal components which added each other, and we knew that the phi or Gauss's law will be given by phi is equal to closed surface integral E dot dA is equal to Q by epsilon naught. Okay, and we knew that the area was this face and this back face added up. So we knew that E times 2 times that area, that is area 1 plus area 2, will be equal to Q by epsilon naught. And we knew that the perpendicular components cancelled each other out. And we knew that surface charge density was Q by A, or simply Q is equal to sigma times A. So we rewrote this Q as E into 2A was equal to sigma times A divided by epsilon naught. The areas cancelled each other out and the 2 came downstairs, and then we can actually write it as E is equal to sigma by 2 epsilon naught. And this is the electric field due to a plain charged sheet. Now let's say we have a hollow sphere. We have a hollow sphere. It is a sphere which is empty inside and it has a thin shell, and we are saying that this is the center of that sphere, and the distance from the center to the surface of the sphere is indicated by R. And one more thing to remember is that the charges are evenly distributed along this surface. Entire region is covered with positive charges. So my question is that what will be the electric field at, let's say, point P here, let's say point P1, and at the surface point P2, and let's say an area outside the sphere, let's say at the point P3. So what will be the electric fields at the point P1, P2 and P3 if the distances are R, capital R and capital R1 respectively? So we are going to find out what is the electric field due to a uniformly charged sphere. For that, again, if you want to know what is the electric field around a particular region, you have to consider a Gaussian surface. So here, since this is a sphere, considering a sphere will be much more easier. So we are going to consider a sphere here. So what this picture will actually look like is that, let's say, this was the center, this was the sphere, and positive charge Q is spread out evenly throughout the surface. And we are going to find out what is the point, what is the electric field at point P, R distance away from the center. And we considered a Gaussian surface. And now we are going to apply Gauss's law, which simply states that, again, phi is equal to closed surface integral E dot dA is equal to Q by epsilon naught. And this is case 1. This is case 1. So Q by epsilon naught, and we know that the area of the sphere is given by 4 pi r square. In this case, it is capital R. So we'll say this is capital R, and we can say that it is E into 4 pi capital R square, which is equal to Q by epsilon naught. So we can say that since there is no charge inside this region, the net electric field will be 0, or the flux will be 0. So we can say that flux is equal to 0 since there is no net charge enclosed in that particular boundary. There is no charge inside the sphere, so there is no charge enclosed inside this area, so there is no flux coming out of that area. That is what is meant by this equation here. And it also states that charges do not reside inside empty spaces. So as a result or as a consequence of Gauss's law, we can say that charges do not reside in empty spaces or within hollow metal spheres. It will only reside in the surface part. The reason can also be explained due to several phenomena, such as charge when being brought inside the sphere, it has a quick tendency to go to the surface as to reduce its state of as to attain a state of minimum energy, and it will create oppositely charged particles at the other end. There is a lot of thing happening there, but the simplest way to explain it is that as a result or as a consequence of Gauss's law, charges cannot reside inside empty spaces. The charge will be distributed throughout the surface only, and that is proven by Gauss's law. So E into the area of the sphere, which is 4 pi r square, will be equal to Q by epsilon naught. And since there is no Q inside that particular area, the electric flux will be equal to 0. And that is case 1. A point inside a hollow sphere. Now we are going to consider a point at the surface. And case 2. So case 2 is a point P2, which is at the surface of the sphere. So we again have a center, we have a sphere where the charges are uniformly distributed, and we are going to consider a point P on the surface of the sphere, and this distance is indicated by the letter small r. So we know that closed surface integral E dot dA is equal to E into A, which is nothing but 4 pi r square, that is small r square, because this distance is denoted by small r. And we know that the electric field is given by the equation kq divided by r square, and k is nothing but 1 by 4 pi epsilon naught into q divided by r square. So substituting the value of E in this particular equation, we can write as phi is equal to 1 by 4 pi epsilon naught into q divided by r square into 4 pi r square. So we can actually cancel pi and pi. 4 pi and 4 pi are gone, and there is an r square here and an r square here. So they cancel each other out, and we can finally say that phi is equal to q by epsilon naught. We have already proved this earlier, but again we found it for namesake. And now we are going to find out the electric field at a point P, let's say point P3, at a distance capital R1 away from the center of the sphere. So again, what do we have to do? We have to consider a Gaussian surface. In this case also, it is a sphere, and it is R1 distance away from the center of the sphere, and we can say that phi is again equal to closed surface integral E dot dA is equal to Q by epsilon naught, which is nothing but Gauss's law. And now we can write this equation as phi is equal to E into closed surface integral dA, which is nothing but the area of the sphere, which is given by 4 pi r1 square, which is equal to Q by epsilon naught. So we'll take this 4 pi r1 square downstairs, and we'll get the equation as E is equal to, this implies E is equal to Q by 1 by 4 pi epsilon naught r1 square. So what did we do? We integrated, and we found out that the area of the Gaussian surface when integrated was nothing but the area of the sphere, which is given by the equation 4 pi r square. And we wrote that down, and now we got the equation for the electric field, which is nothing but E is equal to Q by 4 pi epsilon naught r square. And this equation is very similar to an equation we already saw, which is that is, if we have a point charge, and if we are standing let's say r distance away from that, and we wanted to know the electric field at that particular point, the electric field would be given by the equation kq divided by r squared. Now these two equations look very similar because k is equal to 1 by 4 pi epsilon naught. So what does this actually mean? It means that if we are considering an electric field at, let's say, r distance away from that particular sphere, which is uniformly charged, it doesn't matter if it has n number of q1 plus q2 plus qn number of charges. At a distance away from that center, that net charges will add together and will be acting as if it was a big point charge, point Q. So the electric field experienced by a uniformly charged sphere at, let's say, r distance, x distance, or far away distance from that sphere will be like entire charged sphere is acting as a point charge. So these are the conclusions or applications of Gauss's law you can study. So we found out what was the electric field due to an infinitely long charged wire and an uniformly charged plane sheet. Finally, we considered a uniformly charged sphere, and we considered different points inside the sphere, outside the sphere, and on the surface of the sphere, and we found out what the electric field was there. And this was all found out through Gauss's law. And Gauss's law states that the electric flux through a closed surface in vacuum will be equal to 1 by epsilon times the charge enclosed by that surface, which just means that phi is equal to Q divided by epsilon naught. And that is Gauss's law. So with that, we finish our first chapter, and that is all about electric fields and charges. I'm just lying. I'll come back later with more electric fields and how they interact, and there are even more properties to be discussed. So I'm truthful about the fact that we have ended our first chapter. We'll be moving on to our next chapter, which is electrostatic potential and capacitance. So we'll be discussing more about electrostatic potential, potential energy, and capacitance in that chapter. And we are finished with our first chapter, which dealt with electric charges and electric fields. So I hope you have understood about today's class. It's thank you, and I'll see you all again in the next chapter with more physics. Thank you.